And the material on the exam will be the separation of variables, linear equations, the one that you have to use the integrating factor. So this part using integrating factor, how of x, that's the notation I use, could be different. And then exact equations, which we have to set m and n, then we have to check my equals nx. So those are the three kind of concepts that will be on the exam. If you have accommodations, please contact Professor Gibson, like I would say probably today or tomorrow. That way he can make arrangements for when you come in to take it or where to take it. There's no recitation on the first day after the exam, so enjoy the day off. Make sure when you work on problems, even for homework questions, right? Definitely read the instruction, because the instruction will tell you what you have to finish, what you have to complete. That way you don't have to end up doing a lot more work than you were required, which is a waste of time. Questions? All right, so my plan today is that going through two examples on exact equations and to give you an opportunity to ask questions about the homework. Doesn't matter which one we look at it first, I suppose. Any preference? All right, well, if you don't have any preference, let's go over those two examples first. So the first example I have is we're going to solve this exact equation with initial condition. 3y cubed e to the 3xy minus 1 plus 2y e to the 3xy plus 3xy squared e to the 3xy. There's a lot of x and y's here. It looks complicated. We're just going to follow the procedure step by step. Hopefully it's not that bad. With the initial condition, y of 0 equals 1. So this is the exact equation. Well, I shouldn't say it's the exact equation, but we're going to use the technique of exact equations. So the first step, we still need to check whether it's the exact equation. I used side last time. This time I'm going to switch to f, just to be consistent with Professor Gibson's notation. So suppose that some function f, we're going to say that f sub x, we're going to call it m, which we can find it by just looking at the differential equation. And then f sub y, I'm going to call that n, which we can find from the differential equation. Remember that we want this equation to be in the form of m plus n dx, dy dx equals 0, right? So which part doesn't have the derivative? That will be m. This is the m, and the part multiply the derivative will be n. So that's a 3y cubed e to the 3xy minus 1. And then n will be 2y e to the 3xy plus 3xy squared e to the 3xy. Well, we have to check whether it's an exact equation, right? So the first thing we have to do is we have to take the n expression and then find the partial derivative of m with respect to y. So we want to find m sub y. And then when I do that, because we take the derivative with respect to y, the 3 will be a constant, the x will be a constant. So if we forget about the 3 for y, we just look at this part. It seems like we have to use product rule because that's a product, right? So if we leave the 3 aside, we have y cubed e to the 3xy. We have to use product rule. So 3 times product rule, so y cubed give me 3y squared, multiplied by the second term, e to the 3xy, plus the first term, y cubed, times the derivative of e to the 3xy, so that's an e to the 3xy times 3x minus 0. Any questions about what I did? So I leave the 3, don't worry about it. So now I'm looking at this, I have a product of y cubed and the e to the 3xy, right? So when I use the product rule, it's the derivative of this part, which is 3y squared, times the second part, plus the first part times the derivative of the second one, which is e to the 3xy times 3x. Because we take the derivative with respect to y, so the 3x becomes a constant. And then the negative 1 will give me a 0. Simplify a bit, so we end up with 9y squared e to the 3xy plus, take this 3 multiplied with this 3x, so that's 9x. When we have y cubed, the 9x y cubed, and then the exponential. So that's the partial derivative of m with respect to y. We have to do the same thing for the next part. So n sub x. So now we look at the n, we take the derivative with respect to x. So if we have a 2 there, that's a constant. If we have a y, that's also a constant, right? So those two don't get involved. We just look at the exponential term. And so that will be 2y times the exponential when I take the derivative is the e to the 3xy, but then the numerator, when we take the derivative with respect to x, I get 3y from there. And then what about the second term? Well, the second term has a lot of parts in it. We remember that x is the one that we want to focus on, right? So 3 is a constant, y squared will be a constant, so let's put those aside. Let me use a different color to note what I meant. So if we look at the second term, we can, don't worry about the 3, don't worry about the y squared, just focus on the x. And the e to the 3xy, you can write as 3yx, doesn't matter. But what I really meant is that x is the only variable that we have to pay attention to when we take the derivative with respect to x. So that's a constant. We can leave it aside. This is the x times something, so we have to use the product rule there. So we have 3y squared. And using the product rule, the x will give me 1. So this is 1 times this part plus x times the derivative. So that would be 1 times e to the 3xy plus x times e to the 3xy times 3y. So that's the product rule. In the middle, we use the chain rule. Questions? So, partial derivatives, it could be confusing. You kind of always, when you take the derivative, you kind of have to keep in mind always, like, which one do I really take the derivative of? Everything else, don't worry about, just a constant. So that will be 6y squared e to the 3xy plus 3y squared e to the 3xy plus 3y squared times 3xy, that's a 9xy cubed, e to the 3xy. It turns out that they're the same. So we get my equals nx. So we know that the differential equation is exact. That's a good thing because we know what the solution looks like. So solution to differential equation is going to be in the form of some function with xy being the input equals a constant c. Any questions? So we have to figure out what the function is, right? Well, to find the function, there's a few things that we could use. We know the partial derivative of the function with respect to x is that, with respect to y is this. We have two pieces of information we can use. It's really up to you which one to use. I'm going to use the first one, just because that's, the term seems to be simpler. I think it might be easier. So to find fxy, we're going to use the first information, so we know that f sub x equals m, which is 3y cubed e to the 3xy minus 1, just to rewrite it. And then the f will be the integral of this with respect to x, so that'll be 3y cubed e to the 3xy minus 1 integral dx. The benefit of this one is that we integrate with respect to x. This is the only x we have, so the y here, the 3, we can treat as a constant. Don't worry about it. Only worry about this x. Oh, integrate. So that's going to be 3y cubed integral e to the 3xy dx minus integral 1 dx. Now let's integrate this. So that's a 3y cubed. This is how I do it. You might do it differently. That's perfectly fine. So you can use U substitution, but I'm being a little bit lazy here. So I'm just going to use just directly. So that's going to be times the exponential. When I integrate, I get the exponential. But it's not exactly the same, right? Because if it's the same, then we have a problem. Now we can check if this is the antiderivative, I can differentiate it, try to get this up, but it's not going to give you the same thing. I'm going to erase this work, so if I take the derivative with respect to x of e to the 3xy, I get e to the 3xy, but I also have a 3y extra. So this is an extra term there when I differentiate. Therefore, when I integrate, I need to cancel this term, this extra part, which tells me that when I integrate, I need to have a 1 over 3y in front of it. To this 1 over 3y is to overcome the 3y when we differentiate. And the next term is just going to be x minus x, but don't forget we have to add a constant term, right? Because this is the indefinite integral. So plus some constant term, which I'm going to call h of y, because this constant term doesn't depend on x. It might depend on y. Questions? All right, let me just rewrite it, just organize my work. So the function f x y It's going to equal to cancel the 3, cancel the y, give me y squared e to the 3xy minus x plus this function we don't know yet. Well, pretty close, right? We found that 2 terms, we have 1 term that we don't know. We can try to find it by using the n there, the f of y. If we use that, let's take this function. Let's just find the partial derivative f sub y. That's going to equal to, we're going to have to use product rule. I'm going to do it quickly, but definitely check my work. So product rule on the first term is going to be derivative of y squared, that's 2y times e to the 3xy plus y squared times the derivative of e to the 3xy, that's an e to the 3xy times 3x. And then we have to take the derivative of negative x with respect to y. That's going to be a 0. I'm going to write negative 0. And then derivative of h of y with respect to y, which is the derivative h prime. That's what we get by taking the partial derivative, but that should be exactly the same as what we had before. So recall that at the beginning when we list the m and n, we already have this f of y, f sub y. So that's going to be, I'm just going to copy down what I have. So that's a 2y e to the 3xy plus 3xy squared. So now you can either set them equal, cancel the same term, or you can just, you don't have to set them equal just by looking at them. This is the first term, they match. The second term, they also match. 0, okay, match with 0, that's fine. H prime of y, nothing left, so that will be 0. Which means, recall that h prime of y, remember we took the derivative with respect to y, right? So this is really dh dy. Now, if that equals 0, it means it doesn't depend on y. So h of y has to equal to a constant. I claim that, well, I didn't claim this, someone else did, and we just use it. So we can claim that the c is just equal to 0. We don't have to pick any value, because the c eventually will be absorbed into the c on the right side of the equation. So fxy is equal to y squared e to the 3xy minus x. The h of y is just a constant. We don't need to add it here. You could, but again, it doesn't really matter there. So what's the solution to differential equation? That's going to be just y squared e to the 3xy minus x equals this constant c. Now this c is different from the one I set equal to 0, the different c. So even if you have that c, even if you have it here and here, then eventually will be combined with this. Any questions? Oh, sorry.
So we'll get for the topic of, I'm sorry, that's why is that being equal to n, and then h prime y is that being 0. Is that happen often?
It really depends on the example.
Yeah.
If that happens, it's a great thing, right? You don't have to integrate anything if that happens. I would say not often, but that definitely have a chance to happen.
So the worst would be that the integrate.
Correct. If you, let's say we end up with the 2 there, then we have to integrate in the, that 2y. Right, correct. It just happened to be in this case we get a 0. Good question. So now we need to find C. We're going to use the initial condition that was given, which is y of 0 equals 1. So we're going to put 0, put 1 there, 0 for x, 1 for y. So we got 1 squared e to the 3 times 0 times 1 minus 0 equals c. It turns out that c equals 1. And then the final solution will be y squared e to the 3xy minus x equals 1. This is the implicit form because we have a y in the exponent and also y here. We just can't really write that y equals something. It's not practical. Any questions? All right, if not, so we have a choice. We can go over some homework problems, or we can look at another example. Any preference? Or we can look at another example first, and then look at the homework problems, whichever you prefer. All right, maybe let me go over another example. I think you're going to find it helpful for when you look at the homework problems. So the second example is that we're going to solve initial value problem just like before. Two ty over t squared plus 1 minus 2t equals parentheses 2 minus natural log t squared plus 1 close parentheses y prime. The initial condition is going to be y of 5 equals 0. So we're going to solve the differential equation and then find the c to find the specific solution. That's not it. And at the end, we also want to find solution interval. I mean, we could find the solution interval without finding the c, but that would probably just give us a whole bunch of intervals. So what do? We want to put in the correct form, right? We have to make sure that we have 0 on the right-hand side and the addition between the two terms on the left. So I'm going to move this right-hand side to the left. And that will give me 2ty over t squared plus 1 minus 2t minus 2 minus natural log t squared plus 1 close parentheses and the y prime equals 0. Just to make sure we have 0 here. And I don't like to have a negative here. I want that to be positive. So when you take the negative, bring it inside the parentheses. Or you could, if you want, you can take the equation and multiply by negative 1. That's fine. But I'm going to move the negative inside so that becomes positive. This is negative, that's positive. And by just looking at this, we know which one is m, which one is n, right? Because the part that multiplied by the derivative is n. The one that doesn't have a derivative attached to it, that's n. So I'm going to call this m, which is f sub x. It's going to equal to 2ty t squared plus 1 minus 2t. And then f sub y equals n, which is going to be negative 2 plus natural log t squared plus 1. Actually, I'm going to give you 2 minutes to decide if This is the exact equation. Oh, I don't know why I keep using f of x, so that's f of t. My apologies. Complement of f of x, this is f of y, but we have a t here. So that's the f of t. What do you think? Is that an exact equation? No? Yes? Okay, keep working on it. Don't overthink about those terms when you take the partial derivative. Sorry, n sub t. This is what I'm thinking. When I take the n and I want to find the n sub y, right? So if I just looking at this, to me, only the y that matters. Everything else doesn't matter, right? So this is the 2t divided by t squared plus 1 multiplied by 5, multiplied by y. So you can just think about this is some constant like a number. If you have a number times y, when you take the derivative, you just get the number, right? So this part is essentially it's a constant term times y. So when we take the derivative, we just get that constant. 2t over t squared plus 1. And then what about the negative terms? Well, there's no y attached to it. So when we think about y being the variable, the t is just a constant. So that's a negative 2t constant. When we take the derivative with respect to y, that's going to go away. Become a 0. So that's all we have. And the end there, when we take the derivative with respect to t, we all know that the constant doesn't matter there. We take the derivative with respect to t here, so natural log of the derivative is 1 over t squared plus 1. But then we have to use chain rule, will give me 2t from the inner function. So eventually they're the same. So we get my equals nt, so that the differential equation is exact, which means that the solution to differential equation is going to be some function with t and y in it equals constant. I just want to say that I like to write like this, just to remind me what the solution looks like. You don't have to write this line. It's just for me that, oh, I have to find this part and that. Okay, so which one do we use? Here's another question for you. I need to find the f there. If I use the first one, if I use the f of t equals m, use the m here, I have to integrate with respect to t to get the f, right? If I use the second one, I have to integrate with respect to y to get the f. Which one do you use? It doesn't really matter. Those take you to the same place at the end, but which one do you think will be easier to integrate to get the f function? The second one? Yeah, probably the second one, right? Actually, that's the third one I will pick because we integrate with respect to y, there's no y here. So when we integrate, we're basically just adding a y at the end. Kind of like if you have f of y equals 5, and then you want to integrate to find f, you just integrate 5 dy. You just end up adding a y at the end. This is like a trick to integrate. So I'll take the second one to find ft(y). So f of y equals -2 plus natural log t squared plus 1. F equals integral -2 plus natural log t squared plus 1 dy. F equals -2 plus natural log t squared plus 1 y plus some constant term. Again, here you have to be careful. When we write these as a constant term, it just means that it's constant relative to the variable that we differentiate with or integrate with. So it's constant means that it doesn't depend on y. It could depend on x, so I'm going to call it h of x, being the constant term. Okay, so how do we figure out what that term is? Well, we use fy to get to this point. That means we can use f sub x, the m there. So let's find the partial derivative of f with respect to x. So f sub x is equal to, f sub t. Goodness. So when we take the derivative with respect to t, this is a constant, don't worry about the y. We only need to take the derivative here with respect to t. So 0, this is a derivative from natural log. So we end up with 1 over t squared plus 1 times 2t. And we still have the y outside. It doesn't depend on t, so it stays as a constant. And then the h prime of t, my goodness. So plus h prime of t. And then we can take this and then compare with what we had. So recall we had f of t equals m, which is 2ty over t squared plus 1 minus 2t. So we look at those two and compare them. So here we have really just 2t over t squared plus 1 times y. That's what the first term is. So the first term matches, and then we look at the second term. We have h prime and we have negative 2t. They must be equal. I know that Professor Gibson probably set this part equal to negative line and then cancel the terms that can be canceled. Whatever is remaining, we should then have the same. So we can find h of t by integrating again. So that's just going to be t squared plus a constant. Again, this constant we can see that's just going to equal to 0. We don't need a constant at all. We're going to end up with a constant at the end. Any questions at this point? I know you're busy taking notes, but let me know if any parts that doesn't make sense. Is it negative t squared? Absolutely. Thank you. Negative t squared. Good point. Thank you. Any other questions? Good catch. So let's just put all this together, right, to write down the function. So fty, that's going to equal to the bracket -2 plus natural log t squared plus 1 y, and then minus t squared. We don't need the c. And then the solution to differential equation is going to be negative 2 plus natural log t squared plus 1, bracket y, that's a product, minus t squared equals constant c. And after this, we have to, well, we solve the initial value problem, right? We have to use the initial value. So to find c, we're going to use initial value, which is y5 equals 0. So if we plug in 0 for y, 5 for t, so we get negative 2 plus natural log 5 squared plus 1 times 0 minus 5 squared equals c, and it's obvious to you that this bracket, whatever that is, right, don't worry about natural log of 26, we don't know what that is, it doesn't matter. That times 0 is going to be 0. So we get c equals minus 25. Any questions? So let me write down the actual solution, which is negative 2 plus natural log t squared plus 1 y minus t squared equals negative 25. So you probably think, oh, is this the implicit solution or is it explicit? Well, can we rewrite it? Right? I'm going to try to solve for y, see if I end up with troubles. So if I solve for y here, move the t squared to the right hand side, divide by the bracket. So I got y equals t squared minus 25 divided by negative 2 plus natural log t squared plus 1. It looks like that's okay, right? We didn't really run into trouble there. So the solution is actually explicit. Well, at least we could put in the explicit form easily. What about the solution interval at the end? This is the last part we have to talk about, then we can look at the homework problems. The way I look at it, when we find the solution interval, we just look at this function y, right? If you look at it, you have a natural log, you have to be careful, you want whatever inside the natural log to be positive, so t squared plus 1 has to be positive. See if that gives us any restriction on t. Now, it turns out that that's always going to be the case, right? Doesn't matter what t is, when you square that, you get some number greater or equal to 0. When you add 1, so together the sum is going to be greater or equal to 1. It's always greater than 0, that's what that does. That information, that condition doesn't tell anything about t. Well, another thing you have to worry about is the denominator. You have to make sure that negative 2 plus natural log t squared plus 1, that cannot equal to 0. If that's equal to 0, we got a problem. Okay, so how do we solve for t there? We just solve it as if we have an equation, right? We move the 2 to the other side, so we get natural log t squared plus 1 cannot equal to 2. Add a base e to both sides, so t squared plus 1 cannot equal to e squared. You probably remember that e is about 2.7-ish, around 2.7. E squared is about, I don't know, a little bit less than 9. Just assuming something less than 9, right? And then minus 1, so t squared cannot equal to e squared minus 1. And then t cannot equal to plus minus square root of e squared minus 1. To be honest, I don't know what e squared minus 1 is, but I know that this number is less than 3, so that's 9 minus 1, 8, so this together should be less than 8. But we can just round it to 9, for example. It's somewhere there. So this is going to be somewhere around like maybe between 2.5 and a 3. I just say 2.6-ish. We don't really need to know what it is, we can just estimate. So that tells us that the solution at the end cannot equal to negative square root of e squared minus 1, cannot equal to positive square root of e squared minus 1. And this is about just estimating about negative 2.6 This is about positive 2.6 to estimate. So the interval could be this part. It could be between them. It could be to the right. If we don't have an initial condition, all three intervals could be the interval solution. But now we do have a solution, right? We have the specific solution with initial condition. What do we use? Y of 5. So since we use y of 5 equals 0, so that means t equals 5 must be in the interval. So if you look at it, we need an interval that including t equals 5, which is this part, because that's the right direction point something. So the solution interval is going to be positive square root e squared minus 1 to positive infinity. Any questions about finding the solution interval? Sometimes it's not easy. For example, the previous example, we didn't find the solution interval, right? Because we couldn't just write as y equals something, make it work. That's why we left it there. Questions? How about homework problems? I don't know if you have any chance to look at the homework problems. Any questions from there?
For that right there, why don't we make the use that handle you wrote the last on the left there? Why can't you just keep it as the diagram you wrote on the right?
Over here?
Yeah.
Like the y could use this.
Or why can't you just say t to 9 equals plus or minus?
Right. That's true. So t cannot equal to this for, doesn't matter what c is, doesn't matter what the initial condition is, right? So if we don't have an initial condition, we're just going to be saying like, oh, okay, the solution interval could be this one, or this one, or this one, right? Could be any of the three. Just cannot be equal to those two particular values. But the tricky part is that the solution, the specific solution we found at the end, by using the initial condition, we found out that this is the solution, right? Yeah. That solution is only valid for this interval, because this interval will include the initial condition equals 5. Right? Yeah. If we don't have this initial condition, so the final interval will be just, it's better to write as like 3 intervals instead of inequalities. Yeah. So, good question, good point. Any other questions? How about the homework? I know you probably haven't studied yet. Let me just take 2 minutes. I promise you I'll let you leave early. And that's a one question asked by someone else in a different section was number 4 there. I just want to point out how you begin with that problem. So you have dy dx equals x plus 5y, and we want to solve this using the linear equation method with the integrating factor. So we want to have the equation to be in the form of y plus pxy equals f of x. So that's the setup if you want to use the integrating factor correctly. So the first thing we're going to do is that we want to leave the derivative by itself, and then we want to have something times y next to it, and then f of x on the other side. So basically we need to move this to the left. So we get dy dx minus 5y equals x. So the x we can leave it. So from here, we have, this is a p of x, this is the f of x. And then you can follow what we did after that by multiply by r on both sides and to carry out the steps. Does that make sense? It's actually relatively easy because P is just a constant, so if you use the bracket formula for R, that shouldn't take too long. I also want to mention that, and I'm going to let you finish this. You should try it. It's a good, good practice. From number 5 to number 9, you're supposed to use the technique that we use. Well, you're supposed to see if the differential equation is exact first. I can tell you that one of them is not exact. And you don't even have to solve it. Only the one that's exact equation that you can solve it by using the technique. So that's just an instruction. I did not make it up. So I said I'll let you leave early, and I do. It's 2.5 minutes early. I'll see you on Tuesday. Good luck. The exam is on Wednesday. Over here?
Yeah.
Oh, so in the homework from number 5 to number 9, you're supposed to check whether the equation is exact. If it is, you're going to follow the exact equation technique. If it's not, just leave it. And one of the problems is not exact, but you have to find out which one.
Right.
Yeah. All right, take care, and have a wonderful weekend. I'll see you next week. Take care.